Chapter 3.3, Properties of Logarithms. So in this chapter, we'll be looking at various properties that apply to logarithms that we can use to solve logarithmic equations. These properties are going to be highly reminiscent of the properties that we have for exponentials. So if you are rusty on your exponential properties, I really would suggest looking into that or asking me about it. So the product rule for logs first is log base b of m times n, so something times something else, is equal to log base b of m plus log base b of n. So essentially we can take multiplication inside of our logarithm and bring it outside as addition. So we can separate our log into two things. So a very common type of question you can be asked about logarithms is simply to expand them, which means to take a logarithm with multiplication, division, exponentiation, etc. that we'll see later, and then break it apart into several different smaller pieces. So here, in order to expand the log, all I have right now is multiplication. I have 30 times x and x times 3x plus 4. So I have three things being multiplied together. And so I can break this into three pieces. Notice that when I do so, the base stays the same the whole time. It's always log base 3, like so. So then, once I have that broken apart, I can actually go a little bit further if I wanted to break down this log base 3 of 30. If it were, for example, log base 3 of 9, it would be equal to 2, and I would want it simplified in that way. Log base 3 of 30, if you plug it into a calculator, you would get some sort of number. It's going to be 3 point something, some ugly irrational number. So that's not really what I want. But you can break it down further into its factors. So 30 is equal to 3 times 5 times 2, so we can make this log base 3 of 3, log base 3 of 5, log base 3 of 2, and then log base 3 of 3, well, that's 1. So if you wanted to break it down as far as possible, we could make it like this. It's not necessarily a requirement, though, but it can help you get more of an idea of what's going on and break it down further, how we have this 1 plus these other things. Lower numbers are usually easier to estimate, etc. Our next rule is the quotient rule for logs. So if we have division inside of our logarithm, this becomes subtraction outside of our logarithm. So log base b of m over n becomes log base b of m minus log base b of n. For example, here we have a combination of multiplication and division. I'm going to start out with the subtraction part, with the division turned into subtraction. So I just take the green part of this logarithm and subtract the purple part, specifically the log of the green minus log of the purple. Notice the logs are still there. Don't just get rid of your logs. It's still log base 2 of each piece. And there are two different logs. I'm saying it like this because one of the most common mistakes here is to drop the log or to just turn it into subtraction inside of a single log. That wouldn't make any sense. That would be saying that this is just equal to something subtracted from something, which is not how it works. It's a property of logs. So the log can be split apart, but we're still getting two logs out of it, okay? So we've now broken this down into two separate logs, but we can see that those two separate logs contain multiplication inside themselves. So we've got 15 times x minus 1. And this is, well, obviously, 3x plus 4 times 2 minus x. So each of those can be broken down. So we get log base 2 of 15 plus log base 2 of x plus log base 2 of x minus 1. Minus, notice that there are these parentheses around this whole thing because both of these are being subtracted because it's this whole log. Yes, we broke apart that log, but the quantity itself has to be subtracted off. So it's minus log base 2 of 3x plus 4 plus log base 2 of 2 minus x. Alternatively, yes, you can write it as minus log base 2 of 3x plus 4 minus log base 2 of 2 minus x. I just know that this is something that often gets forgotten. So remember that if you're going to break apart something with the negative, everything should be negative, in the same way that negative x plus 2 means negative x minus 2. Like, we have to distribute that negative. And finally, once again, you can break down log base 2 of 15 a little bit further using its factors. Our third rule is called the power rule for logs. So the power rule takes an exponent inside of our logarithm, so log base b of m to the n power, and says that that is equal to n times log base b of m. So it basically takes the exponent and brings it outside. So if I wanted to expand log base 2 of x plus 3 to the 5th power, now notice the entire x plus 3 is taken to the 5th power. The entire content of the logarithm is being taken to the 5th power. That's important. If it were, for example, log of x squared plus 3, I can't do anything. I cannot bring that square outside because it's not the entire log. I'd have to be able to remove the 3 in some way, which I cannot. So this is equal to just bringing the 5 up front. And so 5 times log base 2 of x plus 3. Now, this is all of the basic properties that we have for logarithms. Power, quotient, product, and then remember the real basic properties we learned in the previous chapter about simplifying log base b of b to the x is equal to x, and log base b of 1 equals 0. So we want to remember these properties. I guess we can also say log, oh, that's interesting. Log, well, let's try that again. Log base b of b is just equal to 1, because it's b to the 1st power, so it just goes along with that other property. So if we have all of these properties now, those are all the basic properties of logarithms. So how can we apply that in reverse, though? If I wanted to condense a log, so all of these are called expanding when I take a log and write it as multiple logs, or I bring my exponent outside of the log, when I'm basically taking stuff that's inside the log and separating it out or bringing it outside, making it a bigger thing. So I've expanded it. To condense a log, we have to have multiple logarithms that all have the same base. In this case, we all have the common logarithm, right? These are all log base 10. The only reason I can do this is because they all have the same base. So I'm going to apply the power rule. That's always going to be the first property, because I cannot, even though I have subtraction and addition right here, I can't apply the rules that involve subtraction and addition until after there is nothing being multiplied by them. So first we apply the power rule. So I look at my powers, I bring them inside. So it's taking the 2 up, making it x squared. The 4, bringing it in, making it x plus 5 to the 4th. Even the 1 over x becomes the power 1 over x, which is not pretty, but we can do that. Next, now we can see that they all have nothing in front of them, and so I can apply my quotient or my product rule, whichever I want to do. I'm going to apply the product rule first. So I'm going to take this addition, and, well, here's where things get a little bit tricky. It's just that I have to remember that, yes, it looks like it's being added to the x plus 5, but this is a subtraction problem, so we have to remember it's really best to sort of think of doing this all at once, product and quotient together. So this is all going to become division, and this is going to become multiplication. So really what happens is the following. Like this. So because this is positive and this is positive, they can be brought together. Anything that's positive, anything with the plus, can be brought together, and the subtraction stays separate so that it can then be made into our division inside of our log. So that can get a little bit confusing. Make sure, again, these look like they're going together, but you have to be mindful of that negative. So you can't just bring these together or else you have changed the problem. So we get, in the end, log, still the common log, still the same base as before, log base 10, of x squared times 3x plus 5 to the 1 over x power divided by x plus 5 to the 4th. And our final sort of formula property of logs is the change of base formula. So the change of base formula can be used to evaluate a logarithm with any base. For any positive real numbers m, b, and n, where n is not equal to 1 and b is not equal to 1, then we get log base b of m equals log of n over log of m divided by log of n over b. And you may be asking, okay, but why would I need to do that? Why does that help me? How does that really help us evaluate a log? Well, essentially, it follows that the change of base formula can be used to rewrite a logarithm with any base as the quotient of sort of nicer logarithms. And you may be asking, well, what's nice about them? And I'll explain that in a moment. But log base b of m is simply equal to natural log of m over natural log of b. Log base b of m is also equal to common log of m over common log of b. All I've done is just replace the n's with e or 10. So why is that helpful? Essentially, what's nice about this property is that not every calculator has an easily accessible log base b where I can change the base function. Scientific calculators generally have a log function, but they don't always have one where you can change the base, or it's not always intuitive to find where that function is. So we use this instead. Essentially, if you're asked evaluate, for example, log base 8 of 4 by changing to base 2, we can do the following. Like, when I look at log base 8 of 4, then I might not necessarily know what it is. I know 8 and 4 are kind of vaguely related, but how? Now, if I change them into log base 2 of 4 and log base 2 of 8, so just take our m right here, and then our original base right here, and I've changed the base. These are both things that you should kind of know how to evaluate by changing it into its exponential. So even if I change this into its exponential, it would have been 8 to the y equals 4, and that's not something I know. But if I have here, the exponential form is 2 to the y equals 4, and I know that's 2. 2 to the y equals 8, and I know that's 3. So log base 8 of 4 is 2/3. So that can also be a helpful way of doing the change of base formula. But alternatively, if I didn't want to try and do it by hand, which you will need to be able to do stuff like this by hand, but if it was a less pretty problem where maybe it's not going to come out nicely and I just want to use my calculator to actually evaluate the log, I could have said ln of 4 divided by ln of 8 and simply place that in your calculator. No, I don't know what ln of 4 is. It's some ugly number, and that's okay. But your calculator knows what ln of 4 is. Your calculator knows what ln of 8 is. Do that division. It's something you can put into any scientific or graphing calculator for that matter, though graphing calculators tend to have the possibility of changing bases. So that's the reason we have the change of base formula, is to make evaluating a little bit simpler, but also specifically to sort of allow simpler calculators to do our work for us. Alright, so here we have a summary of all of these properties. Make sure you have this in your notes. So, properties of logs. We have the product rule. Watch out for this common error. Multiplication on the outside does not become multiplication on the inside. Nor does it become addition on the inside. Addition on the inside breaks your log. You can't do anything. If it's log base 2 of x plus 7, that's it. You can't do anything to that. That stays the way it is. The product rule is about there being multiplication inside of your log. And then it becomes log base 2 of x plus log base 2 of 7. So we don't get multiplication outside of the log. We don't want to deal with addition inside of the log. Similarly, the quotient rule. Common error is to turn that into basically the change of base formula. Obviously, these can't be equal since that's the whole change of base formula. So it doesn't work that way. Division inside becomes subtraction outside. Don't make the mistake of making it division outside. Specifically, it's usually going in the other direction. When you see this and just turn it into division inside, it doesn't work that way. The power rule. Make sure the entire inside of your log is being taken to the power of n. And especially make sure that it's the inside and not the log itself. If the log is being taken to the power of n, this doesn't work. So there's a lot of common errors that come up when evaluating these, so just make sure you're really paying attention. Multiplication inside becomes addition outside the log. Division inside becomes subtraction outside the log. Exponentiation inside becomes multiplication outside the log. I kind of like to, think of this as going a step down. So when we step outside of our logarithm, we go a step down in our order of operations. So if we write out PEMDAS, so exponents, if I start with my exponent, it moves a step down to becoming multiplication. If I start with multiplication or division, it goes a step down to, wow, PEMDAS. There we go. Let's try that again. It goes a step down to addition and subtraction. So just think of it that way, that you're stepping outside, it goes a step down. Now, what's interesting about that, and I don't have a slide for this, but like I said at the beginning, the properties for logarithms really reflect, and it's funny that I say reflect, which I'll explain in a moment, but really reflect how properties for exponents work. So as they are reflections of each other, because they're inverses. So the properties are inverted. Essentially, the similar property for exponents, the product rule, would be b to the m times b to the n equals b to the, not enough room, let's try this again. B to the m times b to the n is equal to b to the m plus n. So now, as we move inside our exponent, we're taking our two exponents together inside, we're actually stepping up in our PEMDAS. So we're going from multiplication, or we're stepping down from multiplication outside to addition, subtraction inside. So it's the opposite, where we went from multiplication in our log to addition outside of our log. Multiplication outside of our exponent becomes addition inside of our exponent. Similarly, we have the property that division outside of our exponent, so we have division of the bases themselves, becomes subtraction inside of our exponent. So again, it's the opposite. And finally, our power rule is we have an exponent outside of our b to the m, so in this sort of format, becomes multiplication inside of our exponent. So we went from exponent down to multiplication, etc. So these properties really do relate to each other they just kind of do the opposite. We're moving from inside to outside versus outside to inside. So again, if you don't know your exponent rules, it's going to be tricky. So those are the three basic rules, so you're definitely going to want to know those. Luckily, this was a fairly short chapter, so we will now be moving on to actually applying all of these properties to solving equations.